This is the Discovery Files podcast from the U.S. National Science Foundation. On April 8th, parts of the United States, Canada, and Mexico will experience a total solar eclipse, when the moon will pass between the sun and Earth and block out much of the sunlight. For a few minutes, millions of people in the path of totality, from Maine to Texas, will be able to experience a total solar eclipse. These total solar eclipses passing over the United States are relatively rare, with the last one happening in 2017 and the next not occurring until 2044. Solar eclipses offer unique opportunities for science, with much of the natural light of the sun being blocked, allowing for observational advantages not usually possible. We are joined today by Carrie Black, a program officer in the Astronomical Sciences Division at NSF, Alain Brizard, professor of physics at St. Michael's College, and Maria Kazachenko, assistant professor in the Astrophysical and Planetary Science Department at the University of Colorado. Thank you all for joining us today. Dr. Brizard, I'd like to start with asking you about something you mentioned in our pre-interview conversation. What is the Saros cycle?
So the Saros cycle was initially discovered by ancient Babylonians that observed that solar eclipses tended to recur with a certain period. The period is equated to the periodic behavior of the orbit of the moon. So the Saros cycle corresponds to 223 lunar cycles associated with the moon crossing the ecliptic plane in a particular direction. Because for a solar eclipse to occur, the moon must be crossing the ecliptic plane at a time when it is either between the sun and Earth, a solar eclipse, or behind Earth, in which case there would be a lunar eclipse. So the Saros cycle was rediscovered later on by Sir Edmund Halley of Halley's Comet fame, based on Newtonian gravitation. He was able to rediscover the cycle. That, of course, facilitates the task of predicting solar eclipses.
Dr. Kazachenko, why is an eclipse a good time to study the sun?
The reason for that is that solar eruptions and solar activity, these all happens in the solar atmosphere. And the solar atmosphere is extremely dim. It's hard to observe. And only during the eclipse we could see the solar atmosphere called corona, and then also the chromosphere, which is a little bit lower down. So only during the solar eclipse you could observe it historically. Now, we have these wonderful tools. We live in the space time, so we have telescopes on ground and in space to learn about both corona and the chromosphere. So nowadays, eclipses are mostly for fun, mostly. Of course, there is some science experience, but now these days I feel that eclipses are more for joy and for outreach.
Before we get into some of the outreach work you and Dr. Brizard will be doing, I want to ask about some of the basics of the eclipse and solar weather. Dr. Black, what is a sunspot?
A sunspot is really cool because they are actually visible. If you have appropriate viewing glasses, you can actually see a sunspot. So they're dark spots on the surface of the sun that are regions of high magnetic field. So very, very concentrated magnetic field that gets super, super twisted up, and they can grow, they can change their shape, they can shrink.
You mentioned magnetic fields. That's another one we hear about, but maybe it isn't exactly clear what it is. So what's a magnetic field when we're talking about the sun?
Well, we're going to get into the basics of plasma physics with this. Plasmas are collections of charged particles. So they're electrically charged particles. And when they move, they create magnetic fields. And the sun is made up of different types of plasma. And it's constantly moving. So it builds these magnetic fields. And the sun has small-scale magnetic fields, and then we have very, very large magnetic fields. So I think everybody or most people are familiar with the idea of a magnetic field from a bar magnet, right? It's a dipole. We call it a dipole. And in quiet times, at solar minimum, the sun is essentially a bar magnet. But because it's not a solid body, it's not made of a solid material, it's made of this plasma, right? It's twisting and moving, and so the magnetic fields get all sorts of twisted up, which is what gives us things like sunspots and coronal mass ejections in the end.
Coronal mass ejections and solar flares, these are also solar phenomena that contribute to space weather. Is that right?
Coronal mass ejections are big solar eruptions that are solar storms, and they have lots of material and lots of electromagnetic field, and those things propagate throughout the solar system. So you can get stormy conditions at planets, and that's why we have space weather. That's what space weather is. It's really important to understand it a lot today, like in today's society, because we have so much that depends on electricity. Our electrical grids, our satellites, our communication satellites, all of these things can be impacted by these big solar eruptions because they are electromagnetic storms, essentially. So when you get buffeted by something like a coronal mass ejection, it can cause charging on your satellites. It can disrupt them. It can cause large electrical currents to run through our power grids and potentially be destructive there as well. A solar flare is another type of solar eruptive phenomenon. So a solar flare is a very bright flash of light that has very, very fast particles. It energizes sort of small amounts of particles to be close to the speed of light, almost the speed of light. So it's different from a coronal mass ejection, which is a very large eruption of billions of tons of material. Solar flare is most noticeable because it does light, very flashy thing.
Dr. Brizard, can you explain a bit about what's going on with these things in the corona and why this eclipse may be particularly of interest there?
If I were able to completely explain what's going on, I would have solved the solar corona problem. The sun is currently entering a phase of maximum activity in terms of the number of sunspots, and each sunspot is a potential location where activity in the form of coronal mass ejections may occur. So it would be tremendously exciting for the general public to see the solar corona at a time that a coronal mass ejection is produced. In a way, the sun is preparing to give us a fantastic display, hopefully. So the corona is essentially a manifestation of the sun producing what is called the solar wind. Each star produces a stellar wind, and that stellar wind, the solar wind, interacts with planets that orbit the sun. The interaction is most often manifested in terms of auroral activity that may become visible at lower latitudes. So during a coronal mass ejection, certainly northern lights could be visible as far south as Washington, D.C., for example.
Where will you be and what will you see during the April 8th eclipse?
I will be on campus in Vermont, guiding faculty, students, and staff through the eclipse from beginning to the end. Once the moon starts to completely cover the surface of the sun, there are various highlights. One of them is called the diamond ring, where, in a way, the sun is shouting, "I'm still here." And then a few seconds later, it's called the Bailey's beads, where the sun is peeking through valleys and mountains, craters of the moon. And then you go to totality. The moon is completely covering the surface of the sun. So that period will last a few minutes, during which we'll be able, hopefully, to see the solar corona, which is one of the last physics puzzles associated with the sun. We still don't understand why the solar corona is so hot. So there are various events. There's there's complex physics going on in the solar corona. So this is just a perfect opportunity for the general public to observe this last mystery associated with the sun.
Dr. Kazachenko, historically there's been a lot of mystery and confusion and fear around eclipses and the sun. But how should people feel about them?
So historically, people, of course, were afraid of the eclipses because nobody knew how to predict them. And you could imagine you're fighting with your neighbor and all of a sudden the light goes off. So, of course, there are so many paintings and historical facts describing how people were surprised by the fact of eclipses. Now, starting about 1800s, people figured out basically how to predict solar eclipses. So lunar eclipses were predicted before, but solar eclipses were predicted first time in 1710 or something. Nowadays, eclipses are very well predicted. We know when the next will happen for the next 1,000 years. But this experience is really unique. And I would compare this experience to childbirth. When you observe your children to be born, this experience is so strong that your whole life is divided into before and after. You suddenly feel like you're part of something big. You feel like you're part of the universe. You suddenly see the electrons, the solar corona. They're shaped by the magnetic field, the electrons flowing along the magnetic fields. This whole experience is so strong and so amazing that you want to do it more and more.
I know you are doing some public outreach events around the eclipse. Can you tell us a bit about that?
I'm going to lead an expedition called Eclipses en la Frontera, funded by NSF Korea. So thanks to NSF for helping us out. And the idea is to bring the joy of solar science to really underrepresented communities where typically scientists don't go. Now, we have a solar physics meeting in Dallas. We have another solar physics meeting in San Antonio. But we are going next to the border to Eagle Pass to basically visit schools there. We're going for 2 days to local schools in Del Rio, one town. We're going to elementary schools, to high schools. We're bringing all the outreach activities there. We're bringing a bunch of telescopes to all these kids. We're going to teach them both in Spanish and English before the eclipse. And then during the eclipse, we'll have a stadium of up to 7,000 people where a local community will join us for a solar eclipse party. And again, we'll bring solar tent with a disco ball where you could see reflection of the solar shadow. We'll have a bunch of telescopes and lots of activities for both adults and kids. So the idea is just to enjoy this wonderful and unique experience together and to learn more about the sun.
I'll ask everyone this question to wrap things up here, but starting with you, Maria, what is your favorite sun fact?
So you know that our sun is very, very far, and it takes 8 minutes for light, for a photon, to get from the solar surface till Earth, right? Now the question is, how long will it take one photon to get from the solar center, which is much smaller than from here to the sun, from solar center to the solar surface? Would it take 8 minutes, 1 minute, or
Probably less.
Probably less? It takes 100,000 years because, and it's very counterintuitive. And the reason for that, it's not the same photon, obviously. I confused you. But it's the photon gets absorbed, caught, and then released, caught and released, caught and released. Mm-hmm. And then it gets into this pots of boiling water, the convection zone. So this whole process gets forever.
How about you, Carrie? What's your favorite sun fact?
My favorite sun fact really is that the sun is a dynamic magnet. I think that is so cool. And the first time I encountered that, it was kind of mind-blowing, to be honest, because I hadn't thought about it, right? You just think about the sun as this like bright, fiery ball, but the idea that it has magnetic fields that change all the time is really, I don't know, it's really kind of inspiring in some way.
Dr. Brizard, what's yours?
The solar cycle is about 11 years. The magnetic polarity of the sun reverses, and it reverses in a semi-predictable fashion. It was first observed by Galileo in 1609, and the magnetic reversal is a lot more predictable than magnetic reversal on Earth. So I think that it is fascinating that the closest star to us still has many mysteries that need to be solved, that are crying for a solution. And yet we've been able to use information about the sun and the neighboring stars to the sun to build a model of the universe. So I think it's fascinating that the sun presents us with enough scientific information to build models of the universe, but still keeps some secrets, some mysteries that are absolutely fascinating.
Special thanks to Carrie Black, Alain Brizard, and Maria Kazachenko. For the Discovery Files, I'm Nate Potker. You can watch video versions of our conversations on YouTube or Roku by searching at NSF Science. Please subscribe wherever you get podcasts, and if you like our program, share with a friend and consider leaving a review. Discover how the U.S. National Science Foundation is advancing research at nsf.gov.